Hi everyone, Morgan here. So we're going to be talking about spectroscopy today. And quite specifically, we're going to be introducing information about visible light spectroscopy. Now, first off, what is spectroscopy? Well, it's the study of electromagnetic radiation. Now, we have a lot of different types of radiation that are useful with spectroscopy. Today, we are just limiting the discussion into visible light. Okay? So, our first question is, why would a liquid be colored? And it's because some component absorbs visible light, and some visible light is reflected. Okay? Some component absorbs visible light. Now, very often when we're talking about the colors of solutions, etc., what we are dealing with is electron transitions in the d orbitals. So there has to be space in the d orbitals for the electrons to jump around in. And that's going to be a major theme of a lab that we do this coming weekend. Okay? So, we have to understand a little bit here about light traveling through a medium. Okay? So, if I shine a light through a beaker of water, the light pretty much goes through. But if I do it through a beaker full of Diet Coke, when the light comes out, some of the intensity is absorbed. So it loses intensity. Now you might be using the word brightness when talking about intensity. Okay? So some of the energy is absorbed. Okay? So what I have here is an outline of a spectrophotometer. Okay? And this is just a pretty general run-of-the-mill outline of what it would look like. We have a light source, which in this case will be what we call white light, meaning a mixture of all wavelengths. Now, that light goes to a lens that focuses it into a prism or a diffraction grating of some type and spreads it out into a classic continuous spectrum. Now, through a control, a little slit here, okay, we can adjust what color light is coming out of this little wall here that blocks it and into our sample. Now, we'll get to a little bit more about this later on, but since our sample is blue, I'm going to hit it with its complementary color, which is yellow. So, blue absorbs all colors except blue. It reflects the blue. Now, it absorbs differently. So, the color it absorbs the best can be determined by looking at your classic color wheel. Now, this is not a good example of a color wheel because of, limited skill with the computer. I've got all the same color, all the same color, all the same color, but this would fade one into the next, kind of bleed together. So actually, if you just open up the control panels on your computer, you can probably find a good color wheel. So it turns out that this blue has a complementary color of yellow. Okay, that's what it absorbs the most. Okay, so we hit it with this yellow that we're going to say has an intensity of I naught. Okay, when it comes out the other side, it will be less, and it'll just have an intensity of I. Okay, and the absorbance is a ratio, or let's try that again. absorbance, okay? The absorbance is the ratio, okay? A equals the negative log of I over I naught. So it's the ratio of how much comes out compared to how much went in. Now that can be detected here and go to some type of an output, okay, where we can read it. Now, typically, historically, the sample container here, which we'll call a cuvette, C-U-V-E-T-T-E, is always 1 centimeter wide. Okay, I have seen ones that are bigger, but that's pretty much the standard for all modern instruments, so 1 centimeter. Okay, so Beer's law governs how much light is absorbed. Absorbance, A equals A, B, C. The more concentrated this is, the more light it's going to absorb and the less that will come out on this side. So C is concentration, or we'll say molarity. B is 1 centimeter, how wide that tube is. And A is going to become important. It is called the absorptivity of the compound. And that is specific and unique to pretty much every compound. Okay? Capital A itself is the absorbance. So what you're seeing here is you have a linear equation. So what we can do, if we wanted to determine the concentration of an unknown, is we will take 4 known concentrations, we'll call them standards, and measure their absorbance. Okay? And we can get this line, and interesting to know that the slope of this line would be equal to A times B up here. Okay, but since B is always 1 centimeter, we don't really concern ourselves with it. Now, if we have an unknown sample that we put into the spectrophotometer and we measure its absorbance, we just come across here till we hit the line, come down, and that's the concentration of the unknown. And that is something that you will be doing in an upcoming lab dealing with copper in brass. Okay, now, we are not going to have to be calibrating our spectrophotometers this time because it is something that's going to be done for you in the video of the lab. But just as a general concept, spectrophotometers still need to have some calibration. So you start out with a known concentration, okay, of a known substance, and you measure its absorbance at a wide variety of wavelengths all the way through visible light. And then that'll tell you at what specific wavelength it absorbs the most. Okay? So we are starting to talk about this. When you have a substance that looks blue, okay, it's going to have a complementary color that's somewhere in the red, orange, yellow range. And when you know the exact wavelength, you can figure out what that is. Okay? So this is just a rough idea of what it's going to look like. Okay? In reality, it looks very different because the colors fade. And face it, with modern technology, this is something the spectrophotometer is going to be able to do for you, so you don't have to worry about it all that much. Okay, so there's your little, short 5-minute primer on visible light spectroscopy. Okay, this is Morgan signing off.